Okay, let's dive right into this explainer. Today, we're taking on one of the absolute trickiest areas in system design: how distributed systems maintain fault-tolerant correctness when parts of the infrastructure inevitably, well, fail. We're going to break down how consensus and transactions actually work together to keep your data perfectly intact across unreliable networks.
To really get why this matters, picture this. You're transferring money between two bank accounts. Now, if both of those accounts live safely on a single machine, our jobs as engineers are pretty easy. But what if those accounts are on completely different machines, sitting across a network, and one of those servers just crashes right in the middle of the transfer? Suddenly, we're looking at a critical engineering nightmare.
You see, on a single node, a transaction is wonderfully atomic. The database simply writes the data, logs it, and it's done. The whole thing succeeds or the whole thing rolls back. But the second we move to a distributed system, we introduce partial failures. That's where a network might drop a packet or a server just hangs indefinitely. One node might actually commit its half of the transaction while the other is completely dead in the water, totally unaware of what just happened.
Think about this basic sequence. We begin, we debit account A, we credit account B, and we commit. We absolutely need a way to guarantee that this exact sequence executes cleanly across multiple servers. Because if the debit succeeds but the credit fails, we've literally destroyed money. And if the credit succeeds but the debit fails, we've magically duplicated money. We need every single node to agree on one final outcome.
So, how do we solve this? Let's look at two-phase commit, or 2PC, a strict system of promises. Historically, engineers brought in a transaction coordinator to manage this. The protocol splits everything into two phases. Phase 1 is basically a voting round before Phase 2 actually enforces the outcome. It's kind of like a minister officiating a wedding. The coordinator asks each database individually, "Are you prepared to commit?" and waits for an "I do" from every single one. If everyone says yes, the coordinator logs that decision and broadcasts the final command to make it official. Now here's the kicker. When a database node replies yes during that prepare phase, it's making an ironclad promise. It's guaranteeing that it can and will commit this transaction later, no matter what. It gives up the right to back out, even if its power cord gets pulled 5 seconds later.
But there is a fatal flaw here. What happens when the coordinator crashes?
Two-phase commit works beautifully, right up until the coordinator goes down. If the coordinator crashes right after collecting those votes, but before sending the final commit message, the whole system just freezes. Database 1 is already voted yes, meaning it promised not to abort, but it never heard the final verdict. So it's stuck in this in-doubt state. It's permanently holding locks on its data, blocking other transactions, just sitting there, waiting for a dead coordinator to wake back up.
And this is exactly why modern high-scale cloud systems run far away from two-phase commit. A crashed coordinator brings everything to a grinding halt. You literally have to get a stressed-out database administrator to manually intervene and fix the stuck transactions. Sometimes systems try to use heuristic decisions to guess the outcome, but honestly, that breaks the exact atomic guarantee we were trying to build in the first place.
All right, so 2PC is out. Let's bring in replicated logs and consensus to the rescue.
At its core, consensus is just getting several nodes to agree on something. But unlike two-phase commit, which demands 100% participation and blocks if even one node sneezes, proper consensus actually guarantees progress. As long as a strict majority of nodes are up and talking to each other, the system agrees on what happened, ignores the dead nodes, and keeps the train moving.
So instead of locking rows and waiting around, a leader node receives a proposal and safely appends it to a log. The followers acknowledge they got it. And the moment the leader hears back from a majority, not everyone, just a majority, boom, it knows the data is safe and officially commits it.
This totally replaces that fragile transaction coordinator. We've shifted from locking isolated databases to appending events to a shared replicated log. A leader proposes the transaction, gets a majority vote, and writes it down permanently. It's elegant, it's robust, and it's built specifically for environments where servers crash randomly.
When you put them head-to-head, it's pretty obvious why consensus wins. It relies on a quorum. If we have a 5-node cluster, we only need 3 nodes to agree. 2 nodes could literally die in the mud, never to return, and your critical banking transfer will still process flawlessly. And if the leader node dies, the remaining majority just quickly elects a brand new leader and keeps right on running.
The magic behind this replicated log is a property called total order broadcast. This means every single functioning node in our distributed bank agrees on the exact, unchanging history of every transaction in the exact same sequence.
no duplicates, no missing events. If all nodes process the exact same sequence of operations, they're all guaranteed to arrive at the exact same final account balances.
Which brings us to our final concept, agreement under failure. In a distributed world, the truth isn't whatever one single node says, it's what the overlapping majority agrees on.
I'm going to leave you with this one final thought for today's explainer. We found a way to achieve absolute distributed correctness. We stopped the lost money and the corrupted data. But requiring strict majority votes for every single transaction introduces network latency. And if a network partition cuts off your majority, the system has to pause to protect data consistency. It just goes to show, there are no perfect solutions in distributed systems, only engineering trade-offs. So what trade-offs are you going to make in your next architecture?